Hello 12s and welcome back to mathematics. In this video we're going to continuing our look at this new section of the normal distribution, and actually what we're going to be doing is we're going to be looking at transforming our normal distribution to a standard normal distribution. And so here what we're going to be looking at something called the z-scores. Now last lesson we looked at a normal distribution, and we talked about how our normal distribution, if we have the mean here, all the scores, and we have our standard deviations above and below. So if we have mu minus 1 standard deviation, mu plus 1 standard deviation, mu minus 2 standard deviations, mu minus 3 standard deviations, and so on this side, but plussing. What we notice is that with our normal distribution like this, there was a pattern where 65% of the scores were between 1 standard deviation above and below. So 68% of the scores were here. 68. 95 were between 2 standard deviations above or below, and then 99.7 were between 3 standard deviations above and below of our mean. But the problem with this is, with our different questions, what we ended up having was different numbers. So if your question had different numbers, so let's say we had one where it's like 90 and then you had a standard deviation of 3, you'd go up by 3 each time. And that's great and all, and we can actually answer these questions with this still. But what we want to be able to do is actually go, okay, is there standardized ways that we can talk about being 1 standard deviation above and below without having to go call it 1 standard deviation above and below or specify these scores? So what we actually do is we use that standard normal distribution. So if you remember, the standard normal distribution is where we have 0 is our mean, and then we have -1, -2, -3. So this normal standard normal distribution. So this is our regular normal distribution. That was we had before, where we distribute it with mu. It's centered at mu and has a standard deviation of it has a variance of mu squared of sigma squared. Here, when we have our standard normal distribution, it's distributed as a normal distribution with a mean of 0 and a standard deviation of 1 squared, or a variance of 1 squared, or a standard deviation of 1. So here, this is what that particular normal distribution curve would look like. Now the reason this is actually useful is because we can refer to these scores, we can refer to these values as being above by 1 or -1, above by 2 or -2, or above by 3 or -3. And we actually call these z-scores. So if you're above by 1 z-score, you are above the mean by 1 standard deviation. If you have a z-score of -1, that means you are below the mean by 1 standard deviation. If you have a z-score of 2, you're 2 standard deviations above, and so on and so forth. So this is actually why using this standard normal distribution is actually quite helpful. But in order for us to actually use this, we actually need to transform our random variables. So here we actually need to use the following transformation, where if we have a score, x is our score, we subtract the mean of our regular random variables distribution and divide that by sigma. So if we want to transform any random variable to be to be the standard normal distribution, what we need to do is use this formula. Now this formula is also on your reference sheet, so you don't need to remember it, I don't think, but we just need to refer to it for these questions. So let's have a look at these questions here. So a continuous random variable, x, has a random normal distribution and a mean of 40, and let me try this again. A continuous random variable x has a normal distribution with a mean of 40 and a standard deviation of 5. The continuous random variable z has a standard normal distribution. P of -2 z P of the random variable z being between -2 and 1 is equal to which of the following? And so here we're trying to relate this to our original random variable. Now -2 to 1, if you have a look at here, that's just going from 2 standard deviations below all the way to 1 standard deviation above. So we want to find this area over here. Okay, so if I wanted to find two standard deviations below, this one's actually quite easy to do without it. If I want to find two standard deviations below with my original one, well, the mean was 40 and we have a standard deviation of 5. So here, two standard deviations below, which is what this minus 2 is telling me, that's just equivalent to P of 40 minus 2 times 5 is less than our standard our random variable, which is less than, well, one z-score above is going to be 40 plus 1 standard deviation of 5. So that's P of 40 minus 2 times 5, which is 30, x 45. And now if you look at the results, look at the answers that we have here. Well, none of our answers is this particular one here. That's an issue. What's happening here? Well, if you remember what we talked about from last lesson, our normal distribution is actually symmetrical. So even though we're trying to find the probability of our standard random variable being between -2 to 1, there's another area under the curve which is exactly the same. If you remember, because of the fact that it is because it is symmetrical, this area that's in red is actually going to be equivalent to this area that's in blue. And so if I find the area from 1 standard deviation below all the way to 2 standard deviations above, that would be exactly the same thing. So here, if I wanted to do P of one standard deviation below all the way to 2 standard deviations above, that's just going to be, well, with my original random variable of x, that would be 40 minus 5, which is 35, and the upper half would be 2 standard deviations above, so 40 plus 2 lots of 5, or 40 plus 10, which is 50, which gives us answer B. And so this is just us relating our standard normal distribution, so z, and using those z-scores of -1 being 2 standard deviations below, and 1 being 1 standard deviation above, and our original random variable. The additional step that we needed to notice was that, once again, the normal distribution is symmetrical. So here, even though our original answer of this probability of -2, z being between -2 and 1, so a z-score of -2 and a z-score of +1, even though that gave us for our original random variable this probability of it being between 30 and 45, that wasn't an answer, but we know that it's our normal distribution is symmetrical, so we can actually just do it in the opposite direction. Okay, let's have a look at this next one. The continuous random variable x has a normal distribution with a mean of 14. I'm going to underline this, so our random variable x and a standard deviation 2. If the random variable z has the normal distribution, so z is standard normal distribution, then the probability that x is greater than 17 is equal to. Okay, here we're trying to find what is equivalent to the probability of x being greater than 17 in our standard normal distribution. So here, what I need to do is use the facts I have originally from my variable x. So here, what I can actually do is I can apply my formula that I had above here. Here, being greater than 17, 17 is the score I'm looking at. So I'm going to just apply this formula here. If I want to find what it's equivalent to, all I need to do is just apply this formula. So here, my score I'm dealing with, so x is my score, and so that is greater than 17. My mean, mu, is 14, and my standard deviation is 2. And so if I wanted to change this into the standard normal distribution, I'm just going to go z is equal to 17 minus, let me just write the formula down. X minus mu over sigma, which is just 17 minus 14 over 2, which gives you 2. And so here, for this particular, is that 2? No, that's 1.5, my bad. So here, if I wanted to find the probability that x is greater than 17, that's just equivalent to the probability of z being greater than 1.5. Okay, now, if you have a look at all my results, z is greater than 1.5 is not on any of these particular scores. And so what I need to do is actually need to go, okay, well, then I just need to refer back to my symmetry. If I've got my normal distribution and my mean is here, and if I had 1.5, actually let's draw this for our our standard normal distribution. I want to find this area over here. Well, that's the equivalent to, on the other end, finding it below this a particular value over here. What would that value be? It will just be on the opposite end, so that's negative 1.5. So here, this is the same as the probability of our standard normal distribution being less than negative 1.5. So that's answer D. Okay, so here we actually start to apply the formula. So this formula is really helpful for us if we wanted to convert our original normal distribution to become like the standard normal distribution. And so here what we had to do was we had to identify a score. So for this one, we wanted to find the probability when our random variable is greater than 17. So our score was 17, and we just put in our mean and our standard deviation that we get given. Then from there, we can actually figure out what is our original probability equivalent to if we were looking at the standard normal distribution. So we were trying to look at the z-scores. So here, what we actually did here was, if we wanted to find the probability that x was greater than 17, that's the equivalent of finding a z-score of bigger than 1.5. And then we noticed that none of our answers was actually z is bigger than 1.5. And so what we had to do was use symmetry. And so if z is bigger than 1.5, it's this area over here, which is equivalent to the opposite area on the other end. So z is less than negative 1.5 z-scores below. Oh, negative 1.5 z-score. Okay, the next example we're going to actually have a go at during our online lesson. So I'm going to leave this one for our online lesson. Okay, let's flip over the page and have a look at a few more examples. Okay, next one here. The weight of packets of Felicity's frozen fish fillets is found to be normally distributed with a mean of 512 grams and a standard deviation of 6 grams. Okay, cool. So here, if we have Felicity's frozen fish. So the weight is the our weight is our random variable, and it's distributed normally and has a mean of 512 grams and a standard deviation of 6 grams. So here it would be 6 squared because we want to put the variance here. Okay, part A. Fong has a packet of Felicity's frozen fish fillets with a standardized weight of Z is equal to 1.75. What's the actual weight of this packet? So if here they tell us it's a standardized weight, which means that it has a Z-score of 1.75. So if we want to find the actual weight, we're trying to find the actual value of x. So if we have a look at the values that we have here, well, we get given that the Z value is 1.75. What other information do we have from the question? Well, the mean is 512. So that's the value for mu. Mu is equal to 512. And we have a standard deviation of 6. So that's sigma is equal to 6. And so what we can do with this question here, is actually we can use the formula that we have for our converting our a regular random variable which is distributed normally to a standard normal distribution. So here this is Z is equal to x minus mu over sigma. Okay, we can substitute our values in. So here, well, I know Z is equal to 1.75 and I want to find the value of x. X in this scenario is the actual weight of the packet because I know that my random variable x is just the weight. So here, x is my weight that I don't know about. So x over here is also my weight, minus mu, which is my mean, so 512, and divide that by the standard deviation. So here, this would be 6. And so if I start to solve and rearrange this, I multiply 6 over. So I've got x minus 512 is equal to 1.75 times 6. 1.75 times 6. That gives me 10.5. And so therefore, x is equal to 512 plus 10.5, which is 522.5 grams. So that's how we can use the actual weight and apply that formula that we've been looking at. So here, this formula helps me convert my original values, so my original mean and standard deviations, and then turn it into z-scores. And it actually helps me backwards as well if I get given the z-score and I want to find the original weight. Okay, let's have a look at part B. Part B. A wholesaler sells boxes of 40 packets of Felicity's frozen fish fillets. Fillets. Fillet. Given that each packet is labeled as containing 500 grams, how many packets in each box would you expect to be under the labeled weight? Support your answer with appropriate calculations. So, what we have here is that this time, instead, we get given that. So here we get told that they sell 40 packets. We're going to be using that in fact in a moment, but we get told that each packet is labeled as containing 500 grams. So that means that our actual weight is 500 grams. So actually, if we get given the actual weight here, we still have the mean from the previous part. We still have the standard deviation. Those haven't changed. What we can do is we can find a z-score from here. So let's actually find the z-score. So z is going to be equal to x minus mu over sigma, which is 500 minus 512 over 6. So that means here 500, let's just put that into a calculator first, minus 512 over 6. So that's minus 2. So what this tells me is that 500 grams, that's just 2 standard deviations away from the mean. So here, if I draw up my standard deviation, draw up my normal distribution, I've got 512 as my mean. And so here, this is 2 standard deviations away. 500 grams, 2 standard deviations away. Now, they ask us to find what's the probability, how many packets in each box would you expect to be under the labeled weight? So we want to find the probability that we are below 500 grams. We want to find the probability that out of the 40 packets, we've got something below 500 grams. Now, if you remember here, this is where we need to use those values that we had from the previous lesson. So here, if we're 1 standard deviation away, that is 68%. If we're 2 standard deviations away, that is 95%. And so what this tells me is that, okay, if that's 95%, that means that the remainder parts, so this part over here and this part over here, that makes up, well, if the total is 100%, that's going to be 5% altogether. And so 1/2, so this part here, that's going to be what? That's going to be just 2.5%. So this has a probability of 2.5%. Okay, well, we haven't finished the question. If they've sold 40 packets and 2.5% of them are below 500 grams, all we need to do, so we just need to take 40 times 2.5%. That's just 40 times 0.025. That means that 1 packet will be below 500 grams. So for this question, we actually needed to use a few things. So firstly, we found how many z-scores we were away from the mean. So here, I put it into that formula and we found that it was minus 2 z-scores. So here we're at a z-score of minus 2. And then from there, we're going, okay, cool. If we want to find the probability that it is under that particular weight, well, I just used my standard deviation values from the last lesson. We know that 1 standard deviation above and below, that is 68%. 2 standard deviations above and below, that's 95%. And then 3 standard deviations, that's 99.7%. And so here, if it's minus 2, well, that means that we are at 95%, that 95% number. Then if I just want to find this highlighted yellow section, we can go, okay, if that part is 95, then the remainder must be 5% altogether. So let me just relabel that maybe. This part here and this part here will get a total of 5% because that should add up to 100. And so half of that, this blue part here is just going to be half of 5%. So that's 2.5%. So if 2.5% of my boxes are below 500 grams, all I need to do is just multiply that with my 40 boxes to tell me that 1 packet out of those 40 will be less than less than that appropriate weight. Okay, cool. So that's how we can use this standard normal distribution formula. Okay, let's have a go through one more question. Hang on, one more question. 2 more questions, and then we'll have we'll leave the rest for our online lesson. Here we go. A biologist found that the length of the wingspan of a sample of butterflies captured from a specific location was normally distributed. The bell curve was shown by the biologist after the wingspan of the butterflies was measured. So here, this is a normal distribution. It's not a standard normal distribution. We don't have, we aren't centered at 0, and we don't have plus or minus 1s on each side. And so here, this is just a regular normal distribution. Okay. Part B. Now, the reason why we start at Part B is because Part A is not actually in the advanced course, so we don't need to worry about it for this particular question. Part B. What would have been the length centimeters of wingspans of butterflies recorded with a z-score of minus 1.3? Okay, so here in part B, we get told that we have a z-score of negative 1.3. And we want to actually find the actual length of the wingspan. So what other information do we have from this diagram here? Well, just by reading off the diagram, we can find the mean. The mean is just the middle value here, so that's 3. So here I'm going to write the mean is going to be equal to 3.00. What else do we have? Well, from this diagram, we can also figure out what the standard deviation was. So a standard deviation, all we're doing is just subtracting those two values. So here, that's just going to be 3.00 minus 2.5. Because we know that every time we go up each time, because it's normally distributed, the key phrase here would be the bell curve, we're just adding or subtracting one standard deviation. So here, if I subtract the 2, that gives me a standard deviation of 0.25. Okay, cool. So by using all of this information, I can actually put it into that formula that we introduced, and I can find the original score, or here, the original length. So here I've got z is equal to x minus mu over sigma. I'm going to substitute my values in. Negative 1.3 is equal to x minus 3.00 over 0.25. So here I substituted all my values in. I can start to rearrange this. So I get x minus 3.00 is equal to negative 1.3 times 0.25. And so the final step is just I add that on. So here negative 1.3 times 0.25 gives me negative 0.325. And so x is equal to negative 0.325 plus 3. So add on the 3. I get 2.675. And so that tells me that the original wingspan in centimeters was 2.675 centimeters. Okay. Part C. Part C. That's the first part. So let's just do a quick recap before I move on to part C. So part B, I get told that they have a z-score of negative 1.3. So I'm just going to write z is equal to negative 1.3. And from my diagram, I can actually pull out the mean by reading off this middle value. So that's a mean. And then also figure out the standard deviation by looking at how far we go up or down by each time we go up by 1 cent, according to that one standard deviation thing. Okay. Part C. The biologist wants to do more research on butterflies whose wingspans are greater than 3.5 and less than 2.50. What percentage of the sample would the biologist use in her research? So let's have a look here at the diagram. We want to look at the part which is greater than 3.5 centimeters and less than 2.5. So let's highlight that on my diagram. That's here, greater than 3.5 and less than 2.50. Okay, so this is where we need to use that standard deviation rule. So 68, 95, 99.7. So let's figure out how many standard deviations away that is. So here, if you have a look, 3.5 is two standard deviations above. So 1, 2, and 2.50 is 2 standard deviations below. 1, 2. And so what this means is, from here to here, that's 95% by using that rule. So 68, 95, 99.7. So if that's 95%, what is the area of that highlighted part going to be? Well, here, this percentage is going to be equal to 100% because the total area is 100 minus that 95%. So here, minus 95%. So here, that shaded part, so above 3.5 and below 2.5, that is just going to be 5% of the scores. Okay, so that's the second part. Here we had to just use our values that we had from last lesson again. Part D. If there were 250 butterflies in the sample, explain why it would be unlikely for a biologist to have found butterflies with a wingspan greater than 3.75. Okay, so this part here. We get told that in the sample there is, there is 250 butterflies. We're going to be using that in a moment. We want to explain why it's unlikely that we found any butterflies with a wingspan greater than 3.75. Okay, greater than 3.75. That's over here and this area up here. So if I want to find that area, we just find the number of standard deviations first of all. So here, that's 3 standard deviations. So between negative and positive 3 standard deviations, so down here and down up here, that's going to be what? 99.7%. And so if I just want to find half, all I need to do is, well, for part D, I just go 100% minus 99.7%, because by doing that, I'll get both of the two ends that are above 3 standard deviations and below 3 standard deviations away. So that will just give me 0.0. Let me try that again. 0.3%. But because we only want half, we just want to take the times up by half. So half times 0.3%, and that will just give me 0.15%. Okay. So if I just wanted this part here, that's just 0.15%. Okay. Well, what do we need to do with this percentage now? We get told that there's 250 butterflies in the sample. So therefore, if we want to find how many butterflies there would be in the sample which have a wingspan greater than 3.75 centimeters, all I need to do is just go 250 times 0.15%. So here, I'm just going to chuck this in my calculator. 250 times 0.15%. That means I've got 0.375 butterflies. So 0.375 butterflies. That's really low. There's very little chance that we're going to actually find a butterfly with that particular value. So here, because it's quite low, we're not going to be able to find that butterfly. Okay, so that's how we answer these questions. So here, we're still using those values that we had from last lesson, 68, 95, 99.7. And so that will help us in actually figuring out what percentage of our scores lie between those values. Okay, I'm going to go through one more example, and then we're going to do the rest in our online lesson. Okay. Here is from the 2015 Math General Exam. The result of 2 tests are normally distributed. The mean and standard deviation for each test are displayed on the table. So here we've got a math and English test, and we've got this mean. So here the mean for this mathematics exam was 70, and the mean for the English one was 75. And standard deviation. So here, instead of using sigma, they've used S. That's okay. We can still adapt to that. And so the standard deviation for math was 6.5, and the standard deviation for English was 8. Christoph scored 74 in mathematics and 80 in English. He claims that he has performed better in English. Is he correct? So what we can do is we can use that formula to actually convert these into Z-scores. The Z-scores tell me how well I perform. So if I have a high Z-scores, that means I'm much higher above the standard, the mean. So let's actually do that for both of my scores. So here, mathematics and English. So what we need to do is we need to use that formula. So here, well, in mathematics, he got a score of 74. The mean, so I'm going to use our notation that we've been using so far. So mu is equal to, well, it's equal to 70 according to this table. That's our average or our mean for our math exam. And the standard deviation, so sigma, is equal to 6.5. Now that I've done that, I'm just going to figure out how many Z-scores here is either above or below our mean. So here, I'm just going to use Z is equal to x minus mu over sigma. So let's sub in our values. We've got 74 minus 70 over 6.5. Let me chuck that in a calculator. 74 minus 70 over 6.5. That gives me 0.615 Z-scores. So he's above the mean, and he is 0.615 standard deviations above the mean for mathematics. Let's do the same for English. Now here in English, what's his score? His score is 80 in English. In English, they had a average or mean of 75, and they had standard deviation of 8, just from the table. Once again, we're going to apply this formula. The Z-score is equal to the score minus the mean over standard deviation. So here, the score was 80 minus 75 over 8. Let's put this in my calculator. 80 minus 75 over 8. And we get 5 over 8, or 0.625. So that tells me he has a Z-score of 0.625. Now, if you've compared these numbers, the Z-score for math is less than the Z-score for English. What this tells me is that he is actually a little bit better. He's been doing a little bit better in English than he is in maths. This Z-score tells me that he is 0.625 standard deviations above the mean, whilst in maths he's only 0.615 standard deviations above the mean. So here, as he has a higher Z-score in English, he is correct. Okay, And that's how we answer these questions. So here we actually need to apply this, converting our regular normal distribution to making a standard normal distribution with z-scores. And the way that we did this was we applied this formula here. Our z-score is equal to our score minus the mean divided by our standard deviation. So that's it for this lesson, Year 12. If you're not sure about anything, feel free to give a comment on Google Classroom or send me an email. I'm more than happy to try and answer your question. And we'll see you in the online lesson. And as always, stay safe, stay healthy, and stay wonderful. And I'll see you in our online lesson. Bye.